Okay, so let's get started. Last week we were talking about acids and bases and structure and bonding. So if you just recall some of the things we covered last week, we talked about orbital hybridization and why in covalent molecules like organic molecules, that in order to be stable structures we have to form hybrids. That gives rise to most stable shapes of molecules, and so sp3 hybridization provides tetrahedral geometry because the electrons are as far apart as possible in 3 dimensions. So the structure of methane, as you can see here, with hybrid orbitals, forming bonds to whatever else it's bonding with an overlap of those orbitals. And an end-to-end overlap of orbitals is called a sigma bond. And you can overlap all kinds of different orbitals in an end-to-end fashion. CH bonds here, as you see, you can have a hybrid orbital from carbon. This happens to be an sp3 orbital, overlapping with an s orbital of hydrogen. That's a sigma bond. Or 2 hybrid orbitals from 2 different carbons overlapping to form a single bond between them. Okay? When we have double or triple bonding, in order to accommodate more interaction between the same atoms, we have to have some of those orbitals unhybridized and left into their normal P shape so they can have a side-to-side overlap. That gives rise to pi bonding. So in the case of an alkene, where you have a carbon-carbon double bond, you have 1 sigma bond overlapping between the carbons and then 1 pi bond which extends above and below the plane. That's indicated by the red and blue there. Likewise, if you have then a 3rd bond, in addition to the single bond created by the overlap of hybrid orbitals, you have to have a p orbital in 1 dimension overlapping sideways and a p orbital in another dimension, 90 degrees overlapping sideways. And that way we have now three shared pairs of electrons between those carbons. Okay, so anybody still have any questions about how bonding and hybridization takes place in these kinds of molecules? Good. We started talking about acids and bases and polar molecules, and when we have electrons that are not equally shared, you can have polarity, and that affects reactivity. So an example of a polar covalent bond, there are many, many examples, which is largely what leads to reactions among organic molecules. And so it's something that we have to really be aware of, the idea of polarization of bonds and which direction those electrons are being pulled towards. Because you're going to have a positive end of a bond and a negative end of a bond. For example, in HF, not surprisingly, the hydrogen is positively charged and the fluorine has more negative charge, right? If you react that with water, for example, you can get an acid-base reaction to occur. So HA, A is just generic for a counterion or an anion. So if you imagine this as a specific acid like HCl or HF, this can react with water or other acceptor of protons to form an acid-base reaction where we've transferred a proton from the acid to the base, giving rise to a conjugate acid and a conjugate base on the right side of the equation. This equilibrium, that reaction could go in either direction, right? That proton could transfer from this hydronium ion to the anion and go backwards. The position of the equilibrium depends on the strength of the acid. Okay, and that's measured by the equilibrium constant. And the equilibrium constant we can also express as a pKa or minus log of that Ka. So again, just to remind you, if the equilibrium constant is higher, then it's a stronger acid reaction to the right. That means the pKa is going to be lower. Okay, so the smaller the pKa, the lower the pKa, the stronger an acid it is. All right. So here, for example, on this slide and the next slide, I'm showing you several different acids from most acidic to least acidic. So here, in this case, HCl has a pKa of minus 3.9. It's a very strong acid. It easily gives up that proton, donates that proton towards a base. Okay, even a weak base like water. If water were to give up a proton, it's not that easy to do, but it can. Its pKa to give up that proton is about 15.7. Okay, around 16. Notice if it acts as a base and gains a proton, the hydronium ion would more easily give up a proton than water. That's all that difference is telling us. But a hydronium ion will give up that proton less easily than HCl. So HCl is a stronger acid than H3O+. Right? So guess what happens if you put HCl into water? The water will be a base, it'll react with the proton, become a hydronium. That's a weaker acid than the original acid you started with. So the equilibrium will shift towards that state. I'll show you a few more. We'll talk a little bit about some of the reasons why acids are stronger or weaker. Yeah, question?
So, I don't know if you'd ever do this, but if you took the stronger acid HCl and put it in with, like, the HF, does HF become a base then, or is something different that happens?
That's a great question. We would choose that one. The question is, if you took HCl and mixed it together with HF, would HF react as a base? I don't think so, because that fluoride isn't very good at donating its electrons, so it's hard to protonate it.
So it's water's kind of
Water is one of those in-between things. So in order to be a base, its electron pair has to be available to be protonated and easily available. That's not so with HF. So good question. There's obviously a lot of gray areas in some of these. You have to think about the reactivity and the availability of it acting as a base as well. But if you were to take HCl and HF and mix them both together in water, you would get more protonation from the HCl than the HF of water. Does that make sense? Here's some more. Now, again, water. We have acids which are weaker than water, and particularly significantly much weaker than water. Obviously, methane is a hydrocarbon, and the pKa refers to being able to take off a proton and form CH3-. That's nearly impossible to do. You can't just take a proton off of methane. pKa of 60 would reflect that. That's measured indirectly through other means, not by direct deprotonating, because you can't do that. But you can deprotonate ammonia, although it's very difficult. You can deprotonate carbons that are next to polar groups a little more easily, and that's also possible. You can deprotonate from things like oxygens or other heteroatoms. Alcohols in water, somewhat similar. Notice if you put carbons on the oxygen, like here is isopropyl alcohol, that oxygen holds onto that proton a little more tightly than H2O does. Okay, but having a good general idea about relative, I don't need you to memorize pKa numbers or anything. But you should know that lower pKa, stronger acid, and be able to predict reaction equilibrium, it'll always lie on the side of the weaker, more stable species. Let me just back up a slide and mention one more thing. The ability to give up the proton of an acid, of anything that's reacting as an acid, forms then the species where that has been deprotonated. Okay? The weaker the acid, the more unstable this anion that's formed would be also, right? If it's hard to give up the proton, it means it doesn't want to go there. So in sort of if you can think about this in the opposite sense, that ammonia is a weaker acid than water, but that means hydroxide would be more stable than this nitrogen anion. Okay, so those concepts actually are sort of tied together, something to think about when you think about reactivity of acids and bases. So then there are several things to think about when thinking about what leads to the strength of acids. Why are some things stronger acids and some things weaker acids? Again, it depends on how easily it can give up that proton. So it depends on the bond strength, right? Bond strength has something to do with it. Okay, so do you have any idea about what things make stronger or weaker bonds? Any of the principles or concepts from general chemistry remember about bond strengths?
Like triple bonds are stronger than a single bond.
Triple bonds are stronger than a single bond. Yeah, all three together would be yes.
Shorter bonds tend to be stronger.
Shorter bonds are stronger. That's right. The closer those nuclei, the shorter that bond, the stronger it is. The better sharing and overlapping of those orbitals. So when you think about a covalent bond, shorter bonds are stronger. So atom size has something to do with bond strength as well. And that's what this chart kind of shows you. HF has a very short bond because fluoride is very small, right? Iodine is much larger. As you go down the periodic table, you're going out further and further, more shells, right? So the electrons are further away from the nucleus. It's a larger atom. This bond length is going to be significantly longer for HI than HF. Consequently, HI will be able to give up its proton easier than HF. Even though another aspect of acid strength is the electronegativity of the atom. Again, remember, if you give up the proton, what's left is an anion. The more stable that anion, the more strong that acid will be. Fluoride is a very electronegative atom. It pulls those electrons very close to it, compared to iodine, which would be much further away. So which of those is the more stable anion? Yeah, it's hard to say. So sometimes these concepts are kind of mixed. That's why we often don't see linear trends sometimes when we think about these, because there's more than one influence on acid strength. Electrons are more stable if they're more spread out and more delocalized. Now, I don't think our book really talks much about resonance, but resonance is important. I'll mention a little bit about that just in briefly about the spreading out of electrons. But certainly if you're just comparing directly difference in electronegativity, carbon, nitrogen, oxygen, fluorine, you do see the trend of increasing acid strength as the atom the proton is attached to is more electronegative. It can more easily give up that hydrogen. The bond is more polarized. The H is more positively charged initially in the polar covalent bond, so giving it up, giving the electrons to the more electronegative atom is easier than to the less electronegative atom. That's why ammonia is much less acidic than water, even though they're somewhat similar and on the same period of the periodic table. Electronegativity has longer through space, through bond effects, even further away from where the proton is coming off. So for example, if you take a look at acetic acid here, acetic acid itself, where X here is hydrogen, has a pK of 4.7. Okay? As you substitute a hydrogen for more and more electronegative atoms, and if you just look at the halogen series, for example, you put iodine there in place of one of the hydrogens, it becomes more acidic, a little bit more acidic. Bromine, even a little more acidic. And fluorine, it's the most acidic of this series. Right? So how do you explain that? What do you think would cause that proton to be easier to give up? The anion must be becoming more stable, lower energy. As you go from hydrogen to fluorine, the anion you generate in this reaction, let's say we react with something like water. Okay, you generate this anion, right? Well, why would making X more electronegative make that more stable? It's one way of spreading out charge through an inductive effect. Remember, as the X becomes more electronegative, what happens to the bond here, the polarization of the bond? between carbon and X. It becomes more polarized. More the electron density is closer to the nitrogen, that leaves the carbon end slightly positive, right? Well, if that carbon becomes slightly positive, that's going to pull more on this bond, pull the electrons towards it. And that's also going to pull the electrons in that bond. So the effect diminishes the further away you get, but it's still, through several bonds, you can feel the effect of pulling electron density towards it. So if X is hydrogen, you don't have this polarization effect. You form the negative charge, it's more stuck on that oxygen. As you put more and more electronegative elements, and then you generate that negative charge. The negative charge is then being spread out more through those bonds by the inductive effect of an electronegative atom. Okay, so that's actually pretty cool. It's one thing we can think about why we see slight differences in reactivity based on substitutions that aren't even changed in the reaction. We haven't changed the CX bond, it hasn't broken or anything when we do an acid-base reaction. And that's a general trend, and it's additive. So if you look at, again, this series, and then you exchange all three of those hydrogens for fluorines. Notice with one fluorine, pK is 2.6. We replace all three of those hydrogens with fluorines. The pK is 0.5. It goes down, becomes more acidic. Okay? This is a general concept that is involved in many different aspects of reactivity, not just loss of a proton. But when we start talking about other kinds of reactions, electronegative induction effects also play a role. Okay? Another thing that has a great effect on acidity is spreading out charges through lone pairs delocalizing into pi bonds. And so when they are right next door, there's something which we call resonance forms that can help spread out the charge. So, and I'm just going to briefly introduce this. Your book doesn't really cover this, but some people might be curious to know why phenol has a pKa much, much lower than other alcohols. Okay, it's more acidic than isopropanol, for example. And that's because this negative charge actually spreads out. It's not localized in one place. And we can draw several different forms of this where that negative charge has moved to that carbon. Oops, what did I do? Shoot. I meant to do something else. Where it's moved to that carbon, that negative charge can be pushed onto that carbon. So that carbon has a significant amount of negative charge. And I'm not going to draw all of them, but you can even push it out here. So push those electrons up to there. So that negative charge actually is more spread out all the way through this ring. And because of that, if you can spread out that charge like across the molecule, that becomes lower in energy or more stable also. That leads to a lot of differences in acidity. That's why there is a difference between ethanol and acetic acid. These molecules both have two carbons. One of them just is an alcohol group, so you just have COOH, and if you deprotonate that, you'd form the O-, right? That negative charge is sitting there just on the oxygen, not going anywhere. It can't go anywhere. It can't be spread out. Notice the pK of alcohol, ethanol is about 16. Compare that to acetic acid, which is 4.7. If you deprotonate acetic acid, okay, you form that negative charge. Okay, but actually that negative charge is spread out onto both of the oxygens. So if you take this oxygen and move that negative charge down to form a double bond here and break that and push it up, you can draw another form. Now, if you could tell the difference between these oxygens, you would see that in actuality what exists is not an isolated negative charge, but kind of like a half a negative charge on both oxygens at the same time. It's spread out. As a matter of fact, another way to kind of represent this is more like that, where that negative charge is spread out among both of those oxygens. Okay, that spreading out of charge has a big influence on acidity. Okay, any questions on that? So, acidity, having an idea about relative acidities and having some idea about what structural features might make something more or less acidic can help us predict reactions. And knowing the pKa numbers, of course, then it's easy. You know, we have an acid reacting with a base. It forms a conjugate acid and a conjugate base. And if you know what the pKa of the acid and the conjugate acid are, you can predict which side that reaction would lie on. Okay? In the absence of actually having those numbers available, I would hope you could take a look at the structures and having some idea about what things give a molecule greater or weaker acidity, and also be able to maybe make some generalizations about where that might lie as well, this equilibrium. So, for example, given the example I just showed you, if I take acetate anion and ethanol, what kind of acid, by the way, which of these would you expect to react as an acid and which is a base? Acetate anion, there's no proton there, so it can't act as an acid here. So the only reaction that can take place is the proton from here transferring to the acetate. Okay. That would form on the other side of the equation the way I've drawn it here, the conjugate acid which would look like that. So just looking at that, which side should the equilibrium of this reaction lie on? Which side would be more favored? Okay.
The left, because the charge is shared.
Exactly, the left. The negative charge here is more stable, lower energy than the negative charge on the right. You can look at it that way. That's one way to look at it, and that's absolutely right. The reaction lies strongly to the left. Another way is if I gave you the pKa's for the acids on each side of the equation. What was the pKa of ethanol was 16, and the pKa of acetic acid was 4.7. Okay? The stronger acid in this whole equation is acetic acid. And it's going to lie on the side of the weaker, more stable species. Okay? Not on the side of the stronger, more reactive species. Right? Everything wants to become more stable and lower in energy. Okay, so that's how we can use some of these concepts to predict reactivity. Oh, I just had I had a slide up there. That's exactly the slide I was telling you about. Okay, so far we've been talking about acids and bases in regards to the Bronsted-Lowry definition, which is an acid is something which gives up a proton, and a base is something which accepts a proton. Okay, but actually that's also a sort of a strict, limited definition because there are other kinds of interactions which we can refer to as an acid-base interaction, which doesn't involve protons. I mean, proton transfer from an acid to a base is a subset of that, but not necessarily. Something we call a Lewis acid, a Lewis base. The definition is slightly different, which includes Bronsted-Lowry acids, but actually includes more than that. So it's a I would say, a broader definition of acid and base. In this case, Lewis defines an acid as a substance that accepts a pair of electrons. A substance which accepts a pair of electrons. So if you're a proton, a hydrogen, a proton, you accept a pair of electrons from water in HCl. And if you're the Lewis base, you're the substance that donates a pair of electrons to form the bond. Okay? Sometimes that involves proton transfer, sometimes it just involves forming a new bond and sharing. So let me give you some examples of how Lewis acid base is a little different than what we've been talking about so far. I will say again, the definition fits with how Bronsted acids and bases work. So here I'll show you, for example, again, HCl plus H2O. Okay. In this reaction, to form hydronium ion and Cl minus, you can define HCl as the Bronsted acid, but also that proton as the electron pair acceptor, as the Lewis acid, because it's an electron pair on water in this case, which is taking that proton. The electrons flow towards the chlorine. Okay. So here, HCl is a Bronsted acid. It accepts a pair of electrons to form a new bond, and H2O is the Lewis base. It gives up a pair of electrons, not gives it away, but shares a lone pair of electrons with something to form a new bond. That formed the new bond to the hydrogen. Okay, makes sense, right? The proton here from HCl has accepted the lone pair from oxygen to form a new bond to the oxygen. The oxygen of water donated the lone pair to form the new bond with hydrogen. Okay. Well, what other ways can we think about this kind of concept without proton? Do you know of any molecules that might be able to accept electrons and not be a proton? Well, if you look on the periodic table, is there one here? If you go to the left of carbon and you see boron, what's the electron configuration of boron? We haven't talked about the structure of boron compounds. So carbon forms 4 bonds, right? Because it has 4 valence electrons, it needs 4 more. Oxygen forms 2 bonds because it has 6 valence electrons, it needs 2 more. Boron has 3 valence electrons. Okay, so how many electrons would it like to have? 5 more to make 8. But if it had 5 more, it would no longer be neutral. Let me write this. Okay, so let's think about boron. Boron has 3 valence electrons. Okay. The electron configuration is 1s2, 1p1, right? I'm sorry, 2s2, 2p1. That's the valence shell. So if you form bonds with boron, you have to be able to share with these electrons, but we only have 3 electrons, so we can only form 3 bonds to be a neutral molecule. So we have molecules like boron trichloride, for example. It can form 3 covalent bonds with 3 chlorines because it has 3 electrons to share. So in each of these covalent bonds, one electron came from boron, 1 from chlorine, 1 from boron, 1 from chlorine, 1 from boron, 1 from chlorine. How many electrons now around boron? 6, right? It doesn't have a filled octet. Although it's relatively stable because it's neutral, if you add more electrons, those electrons have to come from somewhere else. So that means it would have to gain a negative charge if it adds more electrons. The structure actually of BCl3 is planar. So let me ask you this. I'm going to draw this again. BCl3. All three chlorines lie in one plane. If you don't know, the wedged bond means it's coming out of the board towards you, and the dashed bond means it's going away. The bond angle between these are all 120 degrees and flat. What would you say the hybridization of boron is? sp2, that's right. Remember we talked about hybridization in carbon? To make a double bond, it has to be a double bonded carbon has 120 degrees and flat. This is sp2 hybridized. And if you think about it, we started with only 3 electrons. So we can only make 3 hybrid orbitals. S, 1s, and 2 p's. Mixed together to make 3 equal orbitals. What's left then on boron? If the hybridization is sp2, that accounts for 3 orbitals. What's the 4th one? Has to be unhybridized, has to be a p. I'm going to draw it here so you can get an idea. Boron trichloride has an empty orbital. Notice this is not filled with electrons, it's empty. And that's important because what that allows boron to do is accept a pair of electrons. Okay, so if you have a Lewis base around, something with a lone pair of electrons, it can form a bond with boron trichloride. And because there's an empty space, boron wants electrons. Something like NH3 has a lone pair of electrons. And what happens then is, I'll just write it like this, BCl3 with an empty orbital plus NH3. This is an example of a Lewis acid, Lewis base reaction where now we form a bond between boron and nitrogen. All it does is the empty orbital and the lone pair come together and covalently share that. Now, if we do this, the charges on the overall it's neutral, but the charges on the molecule actually has a minus charge on the boron and a plus charge on the nitrogen. Formal charges. If you don't remember formal charges, go back and review formal charges from general chemistry. So that's actually another kind of Lewis acid Lewis base, which doesn't fit. There are no protons involved. Boron trichloride has an empty orbital. It has accepted a lone pair from the nitrogen. So this is a Lewis acid, boron trichloride, and a Lewis base, ammonia. Okay, and that's where this broader definition of acids and bases can be useful because Bronsted, Lowry, or Arrhenius had no way to describe this as an acid and base reaction. But in fact, it's similar because you have something which is accepting electrons, something which is donating electrons. It happens to form now a shared bond between them and form a new molecule complex. Yes, question?
I'm just a little confused how you said it was neutral because it wasn't full of valence electrons, but then we still added.
Because boron only has 3 protons. I'm sorry, only has how many protons? 1, 2, 3, 4, 5 protons. So it has 5 electrons, and the valence shell only 3 electrons. So if you add more, if you fill the octet, then it would have to get electrons from somewhere else and become negatively charged. So to be neutral, it can only form 3 bonds. Okay? Otherwise, you're adding more electrons than what it started with. Does that make sense? So this occurs in a lot of things, especially in this area of the periodic table. Aluminum compounds, similar, that's right below boron. Neutral, it forms 3 bonds, but aluminum trichloride is a good Lewis acid. Question?
Will this change it to be
Absolutely. Great observation. So once you fill that empty orbital, now it has 4 bonds to it, all filled with electrons. It changes its hybridization to sp3. Absolutely right. So notice, again, I start with a neutral BCl3 and a neutral ammonia. Overall, the molecule that's formed is neutral, but there is separation of charge. This is a way in which a Lewis acid can actually activate something and make it more positively charged than before. So ammonia is not positively charged to begin with, but when you form the bond and take some of that electron density away from nitrogen, now you have a formal plus charge on the nitrogen. The reactivity of that nitrogen on the right side of this equation is going to be very different than the nitrogen on the left. The same thing with carbons or oxygens or anything else a Lewis acid might bind to. Okay? So that's the definition. That's why we have this definition of Lewis acid, to get this broader idea of not just proton transfers, but accepting or giving or sharing electron pairs. Okay, any questions on acid-base chemistry in general? So the general concepts, I think we've covered most of the general concepts for acid-base. One thing before we move on, I just want to make clear, as you've seen me drawing a lot of arrows, a lot of different kinds of arrows. And so I want to be clear that in chemical notation, different kind of arrow representations have very different meanings, and it's important not to get them mixed up or confused. So you've seen, for example, an arrow from a reaction, where you have some molecule A or some set of molecules that undergo a reaction and form products B. Okay? A reaction arrow is a one-direction arrow from starting materials to products on the line of a reaction equation. Right? We've seen that many, many times. In acid-base chemistry, we've been talking about equilibrium. So if reactions are reversible, then you have a set of 2 arrows, one pointing in each direction. That refers to an equilibrium reaction. That means A is converting into B, and B can go back and convert into A. Both the things are existing in equilibrium. All right? The arrow I drew when I started to talk about just electrons spreading out actually is a little different kind of arrow. It's a 2-headed arrow. It's not the same as an equilibrium. And again, I'm not going to get into all the concepts of resonance, but a resonance arrow is signifying just a shift in electrons in a pi bond. In actuality, A and B don't really exist. What exists is something which is represented in between by those 2 pictures. So remember I talked about acetate, the anion of acetic acid, where I said the electrons on this oxygen are shared with over to the other oxygen, and then the double bond shifts. Those are just 2 representations, but neither of those really exist. What exists is the hybrid, whatever that blend is in between, so about like a half charge on each side. That's not the same as A and B interconverting. That's A and B trying to show a pictorial representation of what's hard to do with Lewis structure, something in between. So don't confuse those arrows. They are very meaningful. The other kind of arrow we talk about are reaction arrows. Electron flow curve arrows. So when we try to describe how reactions are working, you've seen me draw these acid-base reactions where I have electrons here and they're forming a new bond, and you saw me draw arrows that are curved from the electrons to where those electrons are forming a new bond to. These are describing reaction electron flow. So they're curved wherever we're drawing it, and begin where the electrons are originally and points to where they're forming a bond to, or moving to. So for example, if I have this reaction, A bonded to B, and they break apart and form A plus and B minus, how would I draw the electrons flowing in that process? Using a curved arrow. So the electrons that are changing are the ones in the bond. I'm just going to highlight them here. There are two shared electrons in this bond, right? If I form A plus, that means A is losing electrons, and B minus, then B has gained those electrons. So if I'm going to describe this electron flow, I'll say that the electrons in this bond go to boron, not boron, to B. That leaves B with a minus charge, that then takes away from A, and that's how I would draw that curved arrow. Okay. When I show the acid-base reactions, HA plus some base, I'll just leave generic. The electrons from the base, water, hydroxide, whatever, form the bond with hydrogen. The electrons in the HA bond break to go to A. That's how I would draw those electron flow. Okay. How about this reaction? How do you think I would represent the bottom reaction? Some bond between molecule A and molecule B is breaking homolytically, and one electron goes to each. Any idea how we might represent that with a curved arrow? Yes.
You draw like a split between two arrows going to each A and B.
Absolutely, two arrows going to be A and B, and it's a little bit more than that. When we're talking about only one electron at a time, we actually use a split arrow, but with only half of an arrowhead. That indicates one electron. So you might see in some cases, although most reactions are polar, we might see some free radical reactions at some point, and that's how we represent that. So please try to keep these different kinds of arrows and representations in mind. It does mean something very specific if you use a resonance arrow or a reaction arrow, and then be cognizant of what these electron flow mechanistic arrows are trying to tell us. Just a few examples showing those. There are a lot of different reactions we're going to see over the semester. We've talked a lot about these acid-base reactions, which I just showed, where I could draw the reaction arrow like that. There are other kinds of reactions, though. Here, for example, is a substitution reaction where the oxygen lone pair is actually attacking the carbon to form a new bond at the same time bromine breaks off. Notice how I've drawn the reaction arrows to describe this reaction. Okay, so that's another way, kind of a mechanistic reaction arrow. And many things can be protonated. Here, for example, a lone pair takes hydrogen from HCl. Oops. And can form something like that. So all of these arrows, reaction arrow, electron flow arrows, all help us describe and talk about how reactions take place. Okay? Okay, so that's acid-base, reaction arrows, how we represent structures. I want to move now and start talking about a little bit more details about alkanes and the nature of molecules and what we see in terms of reactivity and structure and things like that. So, alkanes. When we think about organic molecules, of course, simple hydrocarbons is what we think about first. Hydrocarbons are just molecules made up of carbon and hydrogen. And really there's an infinite way in which you can put together carbons and hydrogens to make molecules. Some of the terms we use when we have all molecules with all single bonds between carbons, that's what we refer to as an alkane. Notice the A-N-E ending. We're going to talk about naming. So these endings of the word mean something. If we have molecules with double bonds between them, in the naming of those molecules, we usually use an E-N-E ending because it's referring to alkenes as the general hydrocarbon, which contains double bonds. And for triple bonds, those are alkynes. And then we have special kinds of ring structures like benzene, which we refer to as aromatic hydrocarbons. We'll get to that later in some other chapters. But alkanes, hydrocarbons, really are the basis of organic molecules. They come from mostly petroleum sources. So most alkanes come from crude oil, from old carbon. Oil is distilled into various sizes of molecules generally, which is a mixture of alkanes typically, and probably alkenes and other things. But for example, if you refine crude oil, you get molecules which are very, very light, which are gases at room temperature. Methane, ethane, propane, butane, the short chain alkanes. As those chains get longer and longer, their properties change. They become liquids. They have like light gasolines, heavy gasolines, kerosene, things like that are all different fractions of refining of oil into various groups of chain sizes. Okay, so actually refined petroleum products aren't generally one pure molecule. They're a mixture of different alkanes and probably alkenes and other things. Here are some of the first 10 carbon alkanes and the names. So to give you some idea of what they are when we refer to alkanes as linear or normal alkanes. These are just single carbon chains in a row. The smallest of the alkanes is methane. That's 1 carbon and 4 hydrogens. And remember, since every carbon has to have 4 bonds, the number of bonds where it is in a chain will dictate how many hydrogens are on it. So if it's on the end, for example, if you look at ethane, ethane has 2 carbons. They're both the end of a chain, so there's just 1 bond between the carbons between them, and then 3 hydrogens on each end. Notice the general formula for an alkane with all single bonds. General formula, if you have n number of carbons, then you have 2n plus 2 number of hydrogens. That's a general formula, and that's true for all of these alkanes that are all single bonds. A little bit about the naming. The first 4 alkanes have names which originate, I think, from Greek. Methane, ethane, propane, and butane. Those are probably names that you should just remember. Ethane, the 2-carbon chain. Propane has the 3-carbon chain, and butane has the 4-carbon chain. Once you get past that, then it's more systematic, depending on the number of carbons. So obviously, pent refers to 5. So pentane is the 5-carbon chain. Hexane, 6-carbon chain. Hept is 7. Oct is 8. Non is 9. And deca is 10. So you name these molecules based on the number of carbons in these linear chains. Okay, alkanes can be branched as well. So notice you can have 5 carbons. What's the molecular formula of pentane on the left? What's the molecular formula of this? C5H12, right? Now notice I have a different molecule in the middle. What's the molecular formula for that molecule? One, 2, 3, 4, 5 carbons, right? C5, how many hydrogens? 12. C5H12. Okay, if you don't see that, make sure you take a look at your line formulas and brush up on that. The molecule, the third molecule, C5H12. Notice something? They have exactly the same number of carbons and hydrogens, but they're different molecules. That's something we'll come back to. This is what we refer to as isomers. Isomers. They're isomers because they're made up of the same number and types of atoms, but they're different molecules. Okay? But it does show that you don't have to have molecules which are just straight chain. They can be branched. They can be branched in more than one position. They can be ring structures. Notice here we have a 6-carbon ring molecule. a 5-carbon hydrocarbon molecule, or even you could have larger fused rating systems, and actually it's endless, the number of different kinds of molecules you could make by putting together carbons and hydrogens. So there are lots and lots and lots and lots of just hydrocarbons to think about in terms of molecules. One of the things about alkanes is that they don't really have much in terms of reactivity. Carbon-hydrogen bonds are relatively nonpolar. Alkanes are nonpolar or oily, greasy molecules. They don't do a whole lot. These are essentially the two kinds of reactions that they will typically undergo, and these require lots of energy. Of course, probably the most important reaction of alkanes for society is this first one, combustion. We've been using this reaction for tens of thousands of years, since we first discovered fire. The combustion of organic molecules, and that's an oxidation reaction. So reacting alkanes with oxygen, it generates heat, carbon dioxide, and water. Of course, requires a lot of energy to start it to begin with. Another reaction is also kind of a high energy process. One of the very few reactions alkanes do is free radical halogenation, for example, chlorine. If you generate free radicals of chlorine, it can react to replace hydrogens with chlorines, and you can get chlorinated hydrocarbons. Other than that, alkanes don't do much. It's hard to do reactions with alkanes because we don't have any way to control the reactivity or change the reactivity. That's why it's important to understand that when we try to do chemistry with organic molecules, what we want to have on there are something called functional groups. Something which changes the electronic nature of a carbon, which allows us to form and break bonds more easily. It's hard to break bonds in alkanes. And there are many different kinds of functional groups, but in general, the definition for a functional group is a structural feature in a molecule that has a characteristic reactivity. And we've seen some of it. I showed you an alcohol, isopropanol, a carbon that is attached to an OH. Okay? The thing about an alcohol is that the reactivity that an alcohol imparts to an organic molecule is going to be similar, regardless of what the carbon chain looks like. It could be on 1 carbon, it could be on 10 carbons, but that alcohol there is going to react like an alcohol on any other molecule. So it has a general kind of reaction or reactivity features with just some subtle differences based on the specific structure. Now we can characterize reactions by the type of functional group and the transformations they undergo. For organic molecules, here's sort of some classes of functional groups. When we don't have just single bonds, when we have pi bonds in the molecule, pi bonds give rise to greater reactivity. Actually, taken together, trying to break a CC double bond is completely as harder than breaking a single bond. But the pi bond itself, just breaking the pi bond is weaker than a sigma bond. So you can do more with alkenes than you can with alkanes. There's lots of reactions we can do on the pi bond of an alkene, or of triple bonds. Okay, so we can use those as characteristic functional groups to alter structures and change structures by using the reactivity of the pi bond. Okay, molecules which have other atoms which are not carbon or hydrogen, like, as I said, alcohol, or halides, those will impart reactivity to the molecules and allow us to do different kinds of reactions. So what do you think a bromine carbon bond might be different? The bromine carbon bond, how is that different than a carbon-carbon bond? What would you expect to be different? A carbon-bromine bond versus a carbon-carbon bond?
Weaker.
It's weaker. It's weaker. It's also, very importantly, polarized. The bromine is more electronegative, significantly more electronegative. So this bond is polarized towards the bromine, okay? That means the carbon has some partial, sorry, that's kind of small, isn't it? The carbon has some kind of partial plus charge, and the bromine has some partial negative charge. So that bond is polarized. If you're going to react with something, you want to react with something negative, sorry, that's really small. It'll react on that carbon, as I showed before, to break, to do a substitution. So those kinds of functional groups impart reactivity to the carbon backbone. And we can utilize that. And if you know how one carbon-bromine bond generally behaves, you can predict with any other carbon structure that has a carbon-bromine bond that it might behave similarly. And that's the generality of reactivity that you want to try to get some idea about. For another class of functional groups, there's a variety of functional groups within this class of carbonyls, carbon-oxygen double bonds. These are very important functional groups because they do a lot of different chemistry, and in particular, things like amide bonds, where you have a carbon-oxygen double bond next to a nitrogen. This is essentially the bond which is formed when you take amino acids and join them together. And those are important. Why? Why are amino acids important?
They create your DNA.
Well, not our DNA, but our DNA codes for them, for proteins. Okay, they're protein structures. Essentially everything that makes us up. Connective tissues, the enzymes which do chemistry in our body, they're all made up of proteins, which are long chains of amides that form proteins. So knowing that kind of functionality and reactivity is also very, very critical. Okay, so the functional groups. So think about some ways in which we'll go through in the subsequent chapters, focusing on specific kinds of functional groups, and we'll talk about some of those general reactivities, and then some of the subtle differences based on specific carbon structures within that. I like to think about reactions in really general ways, and I think you could take any chemical reaction of an organic molecule and classify it into one of these four really broad areas. A reaction where you've taken two molecules and combined them together. So you just take two different molecules or two different things, react them together and form one. That would be an addition reaction because we've added things together. Okay, really broad general term. The opposite of that, where a molecule breaks apart into more than one thing, that would be an elimination reaction because we've eliminated part of a molecule or broken it apart. If you take a molecule where a reaction where you've done both at the same time, something came off and something else came on, that's a substitution reaction. Or if none of those things happen and the bonds just rearrange somehow, it's a rearrangement. Rearrangement. And I have some specific examples to show you. Don't worry about knowing the details of these reactions at this point because we'll probably get to some of these later. But here's an example of an addition reaction and shows the reactivity of, say, a double bond. You can add hydrogen with the right catalyst. You can add hydrogen to a double bond and create an alkane from it. So alkene, hydrogen gets added to it, and you generate now the hydrocarbon that's fully saturated. That would be an addition. Two molecules come together to form one. Okay. An elimination reaction, in this case, one of the details of an alcohol functional group is that it's possible to break the CO bond and the hydrogen next to it. So you can actually remove water or eliminate water from that molecule and leave behind a double bond. That's an elimination reaction. There are many kinds of different elimination reactions. That's one specific example. A substitution reaction, where here we have chlorine. It's being substituted by an OH. So we formed a new bond with the oxygen and broken the chlorine bond. This kind of reaction is possible because of the functionality of halides or chlorides, making the carbon more positive. Here you can see nothing has been lost or gained. We haven't added anything, we haven't eliminated anything, we haven't substituted anything, we've just rearranged the bonds to make a new molecule. So those are some specific examples, I think, for these really, really general reaction categories. Also something to think about as we discuss different reactions, because you hear me use some of these reactions. This particular kind of substitution reaction, or this addition reaction. That's referring to this kind of general idea of reactivity. Okay, remember when I showed you the branched alkanes that we have something that is beyond just the linear chains like I showed here. The linear chains of alkanes, you could go to infinity, I suppose, although you can't make that here on the one planet. But, as you get branched molecules, you can have different isomers, the same molecular formula, but they're bonded differently, arranged differently. For example, the normal alkanes or linear alkanes are one area, but branched alkanes can be isomers of those linear alkanes, and the simplest one that you can make isomers of and have different molecules is butane, the 4-carbon chain. So normal linear butane, notice the structure is different, the bonding between the carbons is different, but the properties are different, but the molecular formula is the same. So butane itself boils below 0 degrees Celsius, has a boiling point below 0, about 0.4. Normal linear chain butane. If you have instead the isomer of butane, sometimes referred to as isobutane for obvious reasons, an isomer of butane, it has different physical properties. Not only is it shaped differently, notice you get a change in the boiling point. Boiling point goes down to -10. So isomers can have different physical properties. They are different molecules. And this is what we refer to as a constitutional isomer. This term constitutional isomer. The definition is obviously a molecule which has the same atoms, the same number and kind of atoms, but they're bonded differently. They have a different constitution. That's what we refer to as a constitutional isomer. Okay? So if you have a 4-carbon, yeah, question?
How do you write that? Isobutane.
In a molecular formula?
I know you have to use like C's and stuff. Right? Or, I mean,
Are you talking about a molecular formula or?
yeah, molecular.
Well, that's C4H10.
It's still the same.
Yep.
Butane, so
Same number and number of and kind of atoms. Yeah. There are 4 hydrogens and 10 hydrogens and 4 carbons in both of these molecules. Yes.
So if you're given that number and told the C4H10 told to draw the structure,
Yep.
how do you know which structure to draw?
How do you know which structure, right? That would be a trick question, right? Well, both answers would be correct. I think a question would have to be posed better, like draw all the isomers of C4H10. That might be a better question. But both of these, they have the same number and kind of atoms. They're isomers of each other, but different molecules. Butane, there's only 2 possible isomers. That's why for when we name them, butane and isobutane, it's easy to know what the structure of isobutane is. The more carbons you get in a molecule, the more possible different arrangements of those, the more isomers are possible. That makes naming a little more tricky. For example, here's the 6-carbon chain, hexane. If you take the 6-carbon chain, there are 5 different ways you could arrange those carbons, all to have the same molecular formula, but different structures. Okay, so notice hexane here on the left is just the linear normal hexane, 6 carbons in a row with the rest being hydrogens. if you were to imagine taking the CH3 off of the end and putting it onto the second carbon here, taking one of those hydrogens and switching it, so hydrogen goes to the end, the CH3 goes to the middle, that would give you the second molecule. Okay? If instead you took that from the end and put it on the middle carbon, that would give you the third molecule. Okay, that's different. It's a different molecule than the second one. Hopefully you can see that. What if I were to take that off the end here and put it on this carbon? What would that structure look like?
It would be the same as the second one, just
That's right, this, it would look like this. That would be identical to that one. That would be identical. It's supposed to be equal. I've just rotated it. Okay, so beware, how we draw it, those are exactly the same. I've just drawn it differently on the page. Okay, so be aware of that. If you, instead of the 5-carbon chains where we've moved 1 carbon around, take 2 carbons off and put them in places, leaving a 4-carbon as the longest chain, there are 2 ways in which you could do that. You put those 2 carbons on the same, attached to the same carbon, or attached to adjacent carbons. Those would be different molecules. You can play around with putting them all other places, but each of those would be equivalent to something else on the page. So hexane has 5 different isomers that you could draw from that same molecular formula. Okay, what about pentane, C5H12? How many isomers can you draw of pentane? We have one answer of 3. What are those 3? Okay, so let's see, 1, 2, oops. Where's my pen? 1, 2, 3, 4, 5 carbons. That's pentane, right? So I take 1 carbon off the end. That leaves behind 4 carbons. 1, 2, 3, 4. And I could put that on a middle carbon there. Okay. Or I could put it here. Are those different? No, those are the same molecule. So those are the same. So we still only have 2. Okay, how else could I draw an isomer of pentane? Take another one off and make a 3-carbon chain, and then add 2 to the middle. That's a different isomer. Okay, no other combination of those carbons and hydrogens can I have that with the C5H12 and be a different molecule. Okay, so pentane should be easy to draw all isomers of, right? Well, let's see what I have to do. Well, here's the problem. The more carbons you get, exponentially you increase the number of possible combinations of potential isomers. So you don't have to get that far. What did I say? C6 has 5 different isomers. Okay. C7, 9 different isomers. Once you get to C8, there are 18 different isomers. Different molecules with the same molecular formula. And if you get up to 40, you're already up to 62 quadrillion different isomers possible. Right? That could be a lot of different organic molecules. Okay? A lot of different organic molecules, a lot of different isomers possible. And I want you to think about, we're going to stop here for today, I'll come back to this. Stop here for today. Think about all those possible isomers, and obviously with butane, we have 2, butane and isobutane, but how do you name 62 quadrillion different isomers of the same molecular formula?